Welcome back to The Explainer. So today we're digging into a really interesting problem in AI. It's not about how to build the next great AI, but something maybe even more fundamental. What do you do when your AI gets so big, it just doesn't fit on a single computer chip anymore, right? This is the core question for this whole explainer. We keep hearing about AI models getting smarter, more powerful, but the flip side is they are getting huge. And I mean truly enormous. This isn't just a small snag. It's a massive roadblock that could literally slow down the entire future of AI. So, what's the fix? Okay, to really get a grip on this, we've got to talk about a specific kind of AI, something called a convolutional neural network, or CNN for short. Now, these are the heavy hitters. They're the brains behind all the cool visual AI you hear about. Think about self-driving cars figuring out what's on the road, or AI that can look at a medical scan and spot things with just unbelievable precision. Yeah, these things are the absolute state of the art. And here we go, this is the heart of the problem. To get those amazing results, to get the absolute best accuracy, these CNNs have to be, well, gigantic. We're not talking a little big. We're talking billions of calculations for just one task. That takes up so much memory that, a lot of the time, a single high-end chip just can't handle it. And look at this number. This really drives it home. Nearly 20x. A top-of-the-line model like ResNet 152, one that gets super high accuracy, needs almost 20 times more raw computing power than a smaller, less accurate one. Just let that sink in for a second. That is a huge jump in what we're asking our hardware to do. So what you get is this massive traffic jam-style bottleneck. All that demand for resources just chokes the system. If our hardware can't keep up with how big our AI ambitions are getting, then progress, well, it could just grind to a halt. We have to find a way to run these behemoth models way more efficiently. Okay, so this is where it starts to get really interesting. To try and smash through that bottleneck, researchers looked at a special kind of chip. It's called an FPGA. And no, it's not your usual CPU or GPU. The big deal with FPGAs is that they are incredibly flexible, totally customizable. So what on earth is an FPGA? Honestly, the best way to picture it is like a high-tech Lego board for computer circuits. Instead of getting a chip that's already built for one thing, engineers can basically build their own custom hardware right on the FPGA. They can optimize it to do one specific job, like, say, accelerating a CNN, and do it perfectly. And check this out. This shows you just how powerful that custom approach can be. Researchers built an accelerator on an FPGA. They called it HPIPE. And it did something really clever. It took advantage of sparsity, which is just a fancy way of saying it ignored all the useless, zero-value data in the AI model. And by doing that, it hit a throughput 3.7 times higher than a top-tier GPU doing the same thing. That is an insane performance boost, and it's all because of that custom-built efficiency. So you're probably thinking, awesome, problem solved, right? Well, not so fast, because this super-fast HPIPE accelerator has one major catch. And there it is, the fatal flaw. For HPIPE to do its thing, the entire AI model, all its data, all its parameters, has to squeeze onto the memory of one single FPGA chip. And like we've already established, the best, most powerful models are way too big for that. So we're right back to square one. So how do you solve what seems like an impossible problem? You don't. You change the rules of the game. And that's the breakthrough here. It's an automated system that's kind of like a master planner. It takes that giant AI model and just intelligently splits its brain, dividing up the work across several FPGAs all working together. This automated process, this is really the secret sauce. So you feed it two things, the AI model itself and the specs for your hardware. The system then looks at every single layer of the AI and figures out what it needs. How much processing power, how much memory. Then this clever algorithm gets to work, automatically assigning different layers to different FPGAs. And what comes out the other end is this perfectly balanced, perfectly partitioned model that's ready to go. And the end result of all this is pretty cool. You have 2 or 4 or even more FPGAs all hooked together with super fast connections, and they all work together as one. From the computer's point of view, it just looks and feels like one giant, seamless super accelerator, one that's finally big enough to handle our huge AI model. Okay, but the really clever part is how it splits the model so perfectly. It's not just random. Think of it like a really tricky packing puzzle. You know, like when you're packing a moving truck. You can't just chuck things in anywhere. You have to be smart about it, otherwise you'll run out of space. So the researchers actually tried a few different ways to solve this packing puzzle. Their first attempt, they called greedy forward. This was basically like loading the moving truck from the front all the way to the back, and it didn't work. Why? Because it turns out the last few layers of a CNN are often the bulkiest, the most memory hungry. So the last FPGA in the chain would just get completely overloaded. Their next idea, greedy bidirectional, was smarter. It started packing from both the front and the back at the same time, meeting in the middle. This was definitely better, but every now and then it would still get stuck with one awkward piece that just wouldn't fit. And that led them to the winning strategy. They took that second approach, the bidirectional one, and added one brilliant little twist, a mover function. So when the algorithm got stuck with a piece that didn't fit, the mover would kick in and intelligently shuffle things. It might take a small item from a chip that's almost full and move it to another one with a bit of extra space. And that tiny little shift is just enough to make room for the big, awkward piece. It's this mover that's the real key. It's what solves the puzzle. And maybe the most incredible part, how fast this all happens. This whole complicated puzzle-solving process, it's over in just 3 to 7 seconds. I mean, other methods could take 15 minutes or more just for a small AI model. This is, well, it's practically instant. Okay, so the theory is super elegant, the puzzle solving is clever, but the big question is, did it actually work? You know, in the real world, did all this partitioning actually give them a performance boost? And the answer is a big, resounding yes. Just look at these results for the ResNet 50 model. When they doubled the hardware, going from 2 FPGAs to 4, the performance shot up by 1.8 times. That is almost perfect scaling. We're talking double the chips, you get pretty much double the speed. That's the dream right there. And this wasn't just a one-off. The researchers said it themselves in the paper. For 3 different major AI models, doubling the number of chips gave them almost a 2 times improvement in performance. And the crucial part? They did it without losing any accuracy whatsoever. So how does this new method stack up against the competition? Well, this table is pretty revealing. You might look at this other system from Tobias and his team and think, hey, that looks faster. But there's a catch. They got that speed by cutting corners on precision, which led to a 5% drop in accuracy. This new method we're talking about gets its amazing performance with 0 loss in accuracy. And when you compare it to this other system, it's 4 times faster while using way less hardware. That's a huge win. Okay, so let's boil this all down. What are the big takeaways here? First, that physical limit of a single chip, it's not a hard wall anymore. We can actually split these giant AI models across multiple chips. Second, thanks to this automated system, the whole process is incredibly fast and efficient. And that unlocks near-perfect performance scaling. More chips, more power. And what that really means is we can now run the biggest, baddest, most accurate AI models out there without having to make any compromises. And all this leaves us with one final and pretty crucial question. This technique is a fantastic solution for the massive AI models we have today. But we all know they're just going to keep getting bigger and probably at an exponential rate. So the real challenge looking forward isn't just about finding more clever ways to split them up. It's about something bigger. How do we fundamentally design our software and our hardware to work together from the very beginning, to build a foundation that can actually handle the future of AI?